and I don't even know what I'm saying. So what I got in the habit of doing when I create my my visuals, and sometimes I get lazy and I just grab it from the internet, and then sometimes I really sit down with GeoGebra and I create some nice visuals that I think are, enhance the learning. And so example 1, given u equals 2, 1 and v equals 3, 4, find w equals 3u and a equals 2v. All right. And then going through, and you can see the solution here. It's really weird. I don't know why I starred this one. I had this solution. Maybe starring it was my way of saying, really consider this before moving on to the other one. No, I just accidentally started it, so sorry about that. So 3 times u gives you 6, 3. That's a scalar multiple upon u. And then 2v, scalar multiple upon v, gives you 6, 8. And you can see the size relationship has changed. One is double the length of the other. And then also, and one is triple the length of the other. But also, I said also. So I feel like I should say something beyond that. But really, there's really nothing more to it than that. When you get into linear combinations and actually adding them together, there is an additional consequence. But since this was only talking about scalar multiples, I'm just going to leave it at that. Now, when we talk about adding vectors, the graphical representation is something very specific that I'm looking for you to demonstrate. So, and I will say, so I'm going to caution you on this, and I have the video recording my words, which means I have the evidence. So when you say I never said it, I can roll back the videotape and prove you wrong. So you're not going to be happy when that happens. All right? No, it's not going to happen. You're going to be fine. So on the test, which the date is listed in your syllabus. I can't remember. It's like the 5th or maybe the 4th. It's 2 weeks.
On Thursday.
On a Thursday. It's coming. But the first test is not designed to be the scary end all of the course. All right? Now, we just went over a problem that would make it seem like, okay, we're going to be at this for a while, but I mean, it was just addition and multiplication. So it's addition, multiplication, and perseverance. All right, that's the nature of the beast with this test. All right, except when you get to this problem, because this problem I'm asking for a very particular approach. All right, so I'm going to detail that approach right now, and then you're going to star this, you're going to highlight it, you're going to make note of it, you're going to set reminders for yourself, all that good stuff. Because if you don't follow this approach on the test, you're not going to get much credit. All right, but it's a pretty easy approach. So you're not going to find you're going too far out of your way to get the credit. All right, so let me plot 2, 3. That's not the part that makes it hard. And let me actually get some tick marks in here. I'm just going to go crazy here. That is a triangle. That is not a tick mark. I don't know where that came from. That's so weird. Still a triangle. There's no reason that should have become a triangle. I'm just going to turn the line draw tool off. That's what I'm going to do. So 1, 2, 3, 4, 5 is good enough there. Maybe 1, 2, 3, 4. Yeah, that's good. So I'm going to plot 2, 3. Right about meow. I'm going to draw a vector going to it. I'm going to call that u. 4, 1. Right about meow. I'll do that in blue. I'm going to draw a line going there. Now, it says graphically find u plus v. You know that you could add these two vectors. you know that 2 plus 4 is 6, 3 plus 1 is 4. So you already know the answer, but this says to graphically find the sum of the two vectors. I'm looking for something very particular. All right. So what I want you to do is create a parallelogram out of these two vectors. Right? So we're going to take this vector u. You can do it on your own paper very easily. Take the side of your index card, get the slope, and then shift it over till it gets to that point, and then reproduce that line segment. On that index card, make a little tick mark for the beginning and for the end. Shift it over. This is as close as we'll get to doing a construction in this class. All right? And then draw the line segment. All right? So you're going to make that ray. So for me, let's see, can I duplicate? I'm going to try it. Edit, copy. We'll see in a moment. Come on, give me a page. Okay, give me the whole thing. Okay, that's a complete undo right there. All right, but on my screen, it would be equivalent to taking that line segment and shifting it over so that it's over here. I'll do it as dashed.
Isn't the blue line supposed to be higher up?
Maybe? I mean, it's definitely 4-1 based on my crappy scale. Whether my scale is sufficient, that's a different story, because, you know, me. I mean, maybe not, but you know enough to know that my drawing abilities are suspect. All right, so you're looking at this line segment, do the same thing. Grab the edge of an index card, make little tick marks, get that slope, and then slide it on up. Draw a line segment representing a new one. It's going to connect and form a parallelogram. And then connect the opposite points of that parallelogram starting at the origin. And draw a new vector labeled u plus v. That new vector should actually terminate at 6, 4. All right, and you can verify that, but this is the work I'm looking for this problem. So when you really think about it in the grand scheme, look, I'm not really asking you to do much. You can even fake this work. Like you already have the two vectors. You gotta rough out a parallelogram and draw a line segment that somehow, some way gets you to the answer that you already knew going into the problem was going to be 6, 4, just by adding the two corresponding parts of your given vectors. Like the only way to screw this up is to not answer the question that I'm asking. Graphically find it. If you were to say, okay, 2 plus 4 equals 6, 3 plus 1 equals 4, and then do nothing else, you're sacrificing a lot of free points. All right. When I first put this kind of problem on my test, it was put on as like, they're gonna love me, this is gonna be like the greatest gift ever, and then half the class lost credit on it. I'm like, how could this possibly have happened? They're like, we didn't know what you meant by graphically. I was like, well, when you wrote 2 plus 4 equals 6, fun fact of the day, that's not a graph, just so you know. And they're like, oh yeah, you're right. I'm like, yeah, I am. So, not asking for much. I'm not asking you for you to do this in 3D. Two dimensions is all I'm looking for. All right, so I'm keeping this light. All right, 3 dimensions it gets a little kooky. So, honestly, this is right in my wheelhouse. In my artistic abilities, like I can barely handle this. To draw something in 3 dimensions that'll actually look the way it's supposed to look, there's not a chance for me. All right, so I'm gonna reattach a star to number 3, because that problem, if you had no idea what I was looking for in number 2, that problem is now a little bit more user-friendly. All right? So I'll leave that. So the one suggestion that I made was that you could actually distribute the 2 and make it 2u plus 2v. The other way to handle it would be to actually work off of the first answer, because if you're finding 2 times u plus v, you're looking at a scalar multiple of 2 of the vector sum u and v, u plus v. So what this would mean visually is double the length. I suppose I should turn on a pen. Double the length of u plus v. All right. Now, this is kind of a tricky idea because you'd say, oh, I'll just do that. But that relies on you having done example 2 already. All right, so if this is a standalone problem on a test, you're starting from scratch. Actually, that may or may not be true. Yeah, okay, it is true. I forgot for a second. I couldn't remember if it was the same initial vectors. So if you already had to do 2, then it's just a matter of taking an index card, getting a sense of what the length of u plus v is, and then just extending it by that length again. All right, then you'd have double the u plus v. But if you got to start from scratch, then it really doesn't matter which way you go. All right, so I'm gonna go the other way just because we've already done it the first way. All right, so I'm gonna graph two u plus 2v. All right, so set up set of axes. Positive stuff here, so I can go like this. 2, 3, and 4, 1, right? So 2, 3. Two, 3, and 4, 1. And I can label those U and V, respectively. All right. So now what I want to do is double the length of each of them. So again, a little index card action. So you just, yeah, in some cases you can really eyeball it. I mentioned that last time. Just, it's this long, so I'll make it that long in total. All right. I'm not going to sit there with a ruler measuring things. So as long as it looks like it's in the neighborhood of what it ought to be, then we're going to be in pretty good shape. All right. So that feels right. That does not. That's a little bit better. Still a little out of whack, but I'll take it. Create the parallelogram with these two lengths as their opposite sides. So we're looking at this whole length here. I'll just overlay it here. That's 2u. And this whole length here is 2v. So now I just want to estimate that length. And estimate the other length and create a parallelogram out of it. And that's what we'd be looking at in terms of our final result. Now, the more estimation that you do, the less likely it is that you're going to be able to determine the overall measures just based off of the graph. So you can expect a fair amount of leeway when it comes to this, as long as you have the right idea. Because these two measures are what I would need. And so in the end, if you kind of, I'll call it legally cheated and said, all right, what's 2 times 2 plus 4 times 2? And what's 2 times 3 plus 2 times 1, you know? Like, that's understandable, all right? Or, we already figured out u plus v, so double it, right? So we'd be looking at 12e. All right, based on the scale of the diagram, I mean, that's a little suspect, but, you know, it's in the neighborhood, I guess. That's the idea. Yeah, because the next page goes into... So you could keep adding dimensions. As long as numbers can keep existing, then dimensions can keep propagating, all right? So the general structure of it, and we have our unit vectors and things like that, but I'm not going to get into that just yet. The general structure is that you have an x-axis, a y-axis, and a z-axis, all right? Here's my x-axis, comes out the page directly, well, directly at you, but it's really more of a perspective drawing. Then you have your y-axis, and then you have your z-axis. So when I'm plotting 2, 1, 3, I'm taking 2 steps in the direction of x or x1, then 1 step in the direction of y or x2, and then 3 steps in the direction of z or x3. All right. Freehand sketches are probably the best way to handle this, just because if you get too structured with it, then you feel confined by those structures, and that can be dangerous. All right, so it's one of those things where you don't necessarily know that that's going to be a thing until it happens. So you take this time to develop this carefully structured scale for your x-axis, y-axis, z-axis, and then you start trying to sketch a plane, and then immediately you realize that you're going to need about 17 more sheets of paper in order to fit that plane, because there's no way it's going to fit on your scale. All right, so what I say is don't even bother with the scale until you figure out the characteristics of the graph. Otherwise, it's going to be game over. All right, so we want to get in the habit of thinking x1, x2, x3. So, like I said, we're going to take 2 steps in the direction of x1. Not going to plot a point. Just going to plot the steps, the tick marks, the relevant tick marks. Then 1 step in the direction of x2, and then 3 steps in the direction of x3. All right? These together, these movements together, are going to give us the location of the point in space. All right? So, what I'm going to do, I have my 2 steps along the x1 axis. I am then going to take or I'm gonna make a movement consistent with the distance associated with the movement along the x2 axis, just from this location. All right. So what I'm gonna do is I'm just gonna make little dotted lines here. That distance is what I'm gonna carve out to the right of the second step along the x1 axis. I'm going to go that distance. So basically the same index card approach I was talking about before, you're going to follow that here. Find this distance and then translate it down here, and then you'll have the appropriate distance away from the x1 axis. And then you're going to do the same thing with the x3 axis. You're going to take that distance and translate it down so that it gets to the tip of that outermost point from the movement away from the x1 axis. So this distance here, use your index card or 2 fingers and estimate that distance. And then plot a point at the end of the line there. And then this would be your point, 2, 1, 3. I'm just taking this distance here and translating it down here. So I'm starting off at 0, 0, 0. Then I'm taking 2 steps in the direction of x1. Then I'm taking 1 step in the direction of 2, which corresponds to this distance. So I'm taking that distance and putting it here, making a little mark to indicate where I am. So now I'm here. Then I'm taking this distance, the distance consistent with x3, and moving upward from there. So we're working with parallels. We're working with distances that are parallel to the given axes. The issue is that it's not going to look like square or rectangular movements. It's going to look like parallelograms all over the place. But that's essentially it. The idea is that this point is actually floating in space. It's hard to kind of reconcile that with what you see here because it looks like it's a point that's right next to this x3 axis, but it's not. All right. What you have to actually do is look at the corner of a room. I'll just take this little corner here. You have x-axis, y-axis, and then z-axis. So what happened was you took 2 steps, 1, 2. 2 steps puts you right here. Then 1 step out put you at this location, right where my foot is. And then 3 steps up, 1, 2, 3. So that point is right here. Okay, but how do you create a 3-dimensional drawing on a 2-dimensional diagram? You can do it. It's just it takes a practice hand. It's not always going to look the way you want it to, and so the more practice you get with it, the easier it becomes. For me, you get that. That's why you use GeoGebra.
Why isn't y-axis the one that goes up?
Because the powers that be decided that's how it's going to be. It's so counterintuitive.
Yeah.
Honestly,
Like I see it, but I have to turn it around in my head.
my thinking is, see if I have a blank piece of paper. I'll just hijack one of these. Nah, these are really nice looking packets. I don't want to do that. I'll just do this. So what somebody said was, you have on a piece of paper, for all these students that have been taking math all these years, they've been writing x-axis and y-axis on that piece of paper, right? So if that's the case, then how hard would it be to just incorporate a z-axis? So then if you were to look at this piece of paper, depending on the angle that you take, you might be looking directly at the x-axis with the y-axis being sideways and the z-axis coming up out of the paper. But what they're looking at is, well, you've already been working with the x-axis and y-axis as a horizontal representation. So let's make Z come out vertically because that'll be most consistent with the way that you've been working in pencil and paper. The problem with that is, yeah, that's how you do it in math class, but math class is limited to a small fraction of the amount of time of your lives. The rest of your time, you're experiencing 3 dimensions in a non-math class sort of way, where the Z-axis takes on a variety of different forms. Length, width, and height. If I'm measuring the dimensions of a figure, if I were to tell you, give me the dimensions of that figure, and you were to say, the length is 2 feet, the width is 3 feet, and the height is 4 feet. And then I turn around to you and say, you know what, that's not acceptable. You transposed the length and the width. You said it incorrectly. No, I got the idea. Because one dimension is a horizontal, the other is a vertical from the 2-dimensional perspective, and the other is jutting out. All right? So you can say it any way you want, but the same idea comes across. My thinking, or at least my understanding, is that somebody decided, you know what, they'll understand it best if we use this approach, and it's just not. It's not the best approach, but it is what it is, and so here we are. Yeah, because it would be a lot. Yeah. Ooh, X, Y. Oh, that looks great. And then have a Z come out this way. You know, like, oh.
Or X2 could be Z, because I see Z as width.
Yeah. Yeah. I'll send them a letter.
So this is the final answer?
So that's the final answer. That's the graph. Yeah. And there's really nothing more to it than that, because when I create the vectors, all you're doing is plotting the points and then connecting them with a line segment. This one I got a little cute. I rotated my axes to give it a little bit of a better perspective, so it doesn't quite look like exactly like what we have up there, but it's the same idea. But let me take you, and this will be the last thing we do tonight. Let me take you through a 3-dimensional case and just show you how not well I'm going to create this graph.
So would this actually be an example of what we would do in the tech assignment, just not handwritten?
Right, exactly. That wasn't even close. Correct. And that one behind it. I'm going to give up on that for a few minutes. So, because obviously that's not working. So, yeah, this is not happening by hand because it's just a disaster waiting to happen. All right. So, I'm going to create my axes. I'm not going to put too much care into labels or anything like that in terms of the scale, at least until I get a sense of where I'm going with this. All right, so it's the x1, x2, x3 axis. And so the coordinates 1, 2, and 3, 1, 2, 3, but it's a vector, so we have to make a vector out of this. And then we have to find the vector sum, so that's a different story altogether. All right, so I'm going to take one step in the direction of x1 along the axes. I do everything along the axes first. All right, you may decide when you get a handle on this, you want to do it some other way. I leave that up to you, as long as it comes out right. But this is how I do it. So at least give my way a shot before you decide it's complete garbage. I don't know. So I create tick marks as I go. And again, index card, a side of a sheet of paper. All I'm doing is I'm taking the length of 2 and translating it down so that the origin is going to go to 1, 0, 0. So this point here, my thumb is going to translate over to that, and we'll have a location to plot just an intermediate point. Right? It's not really a point that's going to be plotted. It's just to give me a sense of what's going on. So this distance here, I could use a pointer. I think, look at the old lightsaber out. So this distance here is going to get translated down here. And in some cases we just eyeball it. In a lot of cases we eyeball it. That's the real truth. You come up with what you think is the right length and you do one of these bad boys. And I feel like a smidge more, maybe another dot. There we go. And then based off this scale, I need to go this many up. All right, from this location. So it's going to put me right about here. All right, so if I'm eyeballing it, I'm looking at something like right in this neighborhood right here. So I'm going to draw a line, a ray, to that location with a nice good looking arrow at the end of it. And I'm going to label that U. And that's our location 1, 2, 3. Alright. Coordinates 1, 2, 3, but that ray is in space. Alright, so again, this works out well because I have a graph at my disposal right here. I have a graph with tick marks and everything. So if I'm plotting 1, 2, 3, I'm going 1 unit in the x direction, and then 1, 2, 3 units in the y direction, and then I'm sorry, 2 units in the y direction, right? So back here, and then 1, 2, 3 units in the z direction. So my point is here, floating in space, right here, connected to the origin with a ray, and that's your vector, right? It's floating out in space, but it looks like if this were x-y axis, this would look like it's, you know, on the same plane as the XY axis, but it's not. It's kind of angled out, so it's kind of hovering in space, but it's hard to get that feel based off of the diagram. I guess if you kind of blur your vision and like tilt your head and maybe hold your breath for 30 seconds, you know, right before you start losing consciousness, it might actually start kind of coalescing into the right diagram. I don't know if it's worth that much trouble though. All right, so 0, 4, 1. So 0 in the x direction, 4 in the y direction. So 1, 2, 3, 4 units in the y direction, and then 1 unit in the z direction. So that's actually a little bit easier, because that's just going to put me 1 unit above. Because if you have a 0 value for x, you're really just living in the yz plane, the x2, x3 plane. All right, so if x is equal to 0, then your x2, x3 axes behave very much like your ordinary xy axes, over and up. All right, so that's kind of a nice byproduct, a little bit easier to work with. Now when I want to graphically find the vector sum, here it's just a matter of doing exactly what I did on the previous page, but you had to get here in order to do that. So this problem is a disaster to grade, which is why I never put it on a test. It's a nightmare. I mean, a wrong answer looks just as good as a right answer, so what's the value in it? I have people faking their way to full credit all the time. So maybe you want it on the test, but I'm taking this out and putting an easier one that you're all going to get right as long as you do it the way I tell you to, so what does it matter to you? All right, so I'm going to create a parallelogram using the same technique as before. Index card, eyeball, whatever. I came to grips a long time ago that there are some people in this world that can draw freehand better than I can with a ruler. So it is what it is. It's just the nature of things. So if that's you, go for it. I've seen some people turn in some work that I was like, man, you're good at math and art. You know, like I get jealous, but then I give them 100 and we move on. So, you know, there's just some really talented people out there. When it comes to art, not me. Right? If I didn't have these tools to work with, I couldn't even do something this nice. All right, so create the parallelogram, draw the ray going from end to end, slap in a U plus V. Somewhere off on the side, tell me what U plus V is equal to. It should correspond with the location, but it's very hard to verify that. 1, 6, 4. I mean, honestly, if you could pick out in 3 space, if you could pick out the coordinates of a hand-drawn diagram of a point in 3 space with any kind of accuracy, without like lots of stuff being given to you in terms of scales, then you're better at this than I am. You should teach the class, I guess, because it's not easy to do. Because the best you can do here is like say, okay, I think maybe we're 1, 2, 3, 4, 5, 6-ish, and then you get the 4, but how are you coming up with the 1? Like you'd have to make some educated guesses in there. It's not really something that would play out very well. So the best you can do when you're looking for a graphical representation of the sum is actually come up with the graph, but you're not going to be able to pull the answer from it. Whereas in 2 space, you can still pull the answer from the graph itself without actually doing the addition. So another reason why those kind of questions are better for a test. All right, so I'm going to put a star on number 6. Same idea as the previous page. You should be able to relatively easily handle. I think it's a reasonable looking typo. All right, so this one is saying find the vector sum of u and negative v. So we don't want to lose sight of that. U plus negative v is what we're dealing with here. Doubled. All right, so I'm going to do it a little differently here. I'm going to find that vector sum u and negative v, but then after I do that, I'll double that resultant vector. All right, so u we're going to leave alone, but negative v, scalar multiple of negative v, is going to be 0, negative 4, negative 1. So it's these 2 vectors that we're going to be adding, u and negative v. All right, so I'm going to make my coordinate axes. That is not what I mean, you can see the tracer, that's not what should have come up. It's a little long, but I'll live with it. All right, so 1, 2, 3. So I'm going to go out 1, 2, 3. The other numbers aren't, I wouldn't say they're outrageous, so I think the scale is okay. So the 1 is fine. This is what 2 feels like, so I'm going to do that off of the 1, so it's going to put me right around here. And then this is what 3 feels like, so I'm going to shoot up 3 from that red dot, and that's going to be my point. And actually it corresponds, the way I have it played out here, with about 2 units up on the z-axis. You could use that as a reference point. This one I think is fine, so it would be about right here. All right, so that's my vector u. Now I need negative v, so that's going nowhere on the x-axis. Then I'm going -4 on the y-axis, so that's to the left. And then I'm going to go down 1 unit on the z-axis. All right. So I can extend my y-axis to the left, going out 1, 2, 3, 4 units. And then I'm going to go down. So left 4, down, the equivalent of 1. Keep hitting the wrong thing. Down 1 on the z-axis, yeah, so equivalent of 1 puts me around right here. All right, so that's going to be the equivalent of negative v.
So where's negative 1? Where you put negative 1?
Where did I put it? I went down 1 unit from
Oh,
the axis, yeah. So negative v is this guy. All right. So the vector sum of those two would be the parallelogram created and the ray extending from the origin to the opposite vertex angle. So I'm going to transpose this vector over, and then I'm going to slide this one up and create that parallelogram. More or less. And then the opposite side. Undo that. So this one is u plus negative v. All right, so that's my resultant vector. All right, so I create the parallelogram out of u and negative v. Origin out is the sum of those two vectors. All right, but I need double that. So I'm going to take that line, that ray, sorry, and extend it out, and then I'll have what I'm looking for. All right, so I did not put my line draw tool on. So we're talking about this one here. That is going to be 2 times u minus v. And that's the graphical representation. Now, in terms of the actual point that that corresponds to, as we know from the last problem that we did, very hard to tell from a three-dimensional graph what the point in space would actually end up being, because I don't know if this vector is living in the YZ plane, or if it's shooting out the paper at me, or if it's shooting into the paper. Like, what are we up against here? So we go by the numbers to find the actual point, but this is the visual representation. So that's the graphical solution. But if we want to find the actual sum, we'd actually still have to do the work. So 2 times, if I add these two vectors together, I'm looking at 1, negative 2, 2, which ends up being 2, negative 4, 4. Now that's one of those things where you're like, yeah, I guess. Like 2 negative 4, 4. Is that what this looks like? I don't know. Maybe. If I go out 2 here, that puts me here. And I get my length of 4, that's gonna shoot me out over here, somewhere in this neighborhood. And then I gotta go up 4. Is that gonna get me directly to where I drew it? I don't know, I did a lot of freehand stuff here, so I'm gonna err on the side of probably not, but it should be in the ballpark, right? That's really what it's coming down to, all right? So as far as a check goes, you know, that's not the most satisfying one in the world, but it's something, you know, as long as you can plot your vector sum and come up in the neighborhood of where your diagram terminated, then at least you could say, all right, I probably did my picture, I made my picture correctly, right? And that's really all I could ask for, all right? But like I said, on the test, I'm gonna give you something in 2D anyway, so. This is more for enriched thinking, I guess. Some of them are obvious, I think, I hope. At this stage of the game, I would love to think that you are comfortable and familiar with things like the commutative and the associative properties, right? That's not unreasonable, right? The identity property, additive identity, right? An additive inverse property. I'm going over these with my Algebra 1 students at the high school, right? But definitely not in the context that we'll be working with them, because we're going to be using matrix operations and vector operations and things like that. But like, they're just starting the journey and they're looking at this like, yeah, that makes sense. Yeah, that makes sense, but why doesn't it work for subtraction? And then we talk about that, you know? Like, well, make up some numbers, throw them in, see what happens. One thing I can tell you is, and this is not always 100% true, but it's a good rule of thumb. If it doesn't work for simple algebra, it's probably not going to work for linear algebra, all right? There are exceptions to that, but it's a good rule of thumb. So commutative property works for addition and multiplication, but not subtraction. So if I switch the order on subtraction, 2 minus 1 versus 1 minus 2, opposite numbers, all right? So if it doesn't work for simple algebra, we would not expect it to work for linear algebra, all right? But then you have other things, like commutative property for, associative property for multiplication. You have a variation on the distributive property, but this is an interesting one, because C and D represent scalars, where U and V represent vectors, and also W when it comes into play. So when you look at something like this, you say, all right, hold on a sec, we got U being distributed against when you're dealing with scalars, and you have U and V also being distributed against when you're dealing with scalars. But what about if you're distributing a vector against another vector? Is that something that can happen? Well, that's an issue, because vector multiplication is a different animal altogether, right? Vector and matrix multiplication works completely differently from scalar multiplication. So these two properties are talking about imposing scalars upon vectors, right? So that's something very important to keep in mind. When we get to matrix multiplication, you'll see it all come together, right? And it's going to be pretty informative, hopefully. That's the plan anyway. The last one is the identity element, or the multiplicative identity property for matrices and vectors. So the issue here is that one is a very misleading one, because one can take on many different forms when dealing with linear algebra. So for now, we're just going to call it one. But when we're talking about an identity, if it's a matrix form, it's not just going to be a singular number, right? But it'll amount to the same thing as multiplying a matrix by one, right? But for now, we're living in the world of vectors. Notation, and this is something that I'll remind you of repeatedly. Just because, anytime you see a vector that's defined as 0, that's known as the 0 vector, if it's a vector in 2 space, if I call it 0, it doesn't mean it's just the number 0. It means it's the vector 0, 0. 3 space, 0, 0, 0. 4 space, you get the idea. All right? So 0, in the context of being a vector, does not just mean the number 0 as a standalone constant. All right? Linear combinations. This is kind of like the beginning of our journey into the theoretical stuff, because when we were dealing with row operations, echelon forms, and things like that, those are skills. Those skills we'll be using to analyze situations that are going to emerge. Like, we're going to talk about inverses, we're going to talk about determinants and things like that. And they're all going to, in some way, shape, or form, come back to the idea of row reduction techniques. All right? But in order to understand real space, all right, so 2 space, 3 space, 10 space, whatever, real space, omnidimensional space, you need to understand the concept of a linear combination, because this is how you span that space, that reality. All right, so it's really just plotting a course, you know. So like, I'm into sci-fi, so sci-fi fantasy. So sci-fi, Star Trek. Sci-fi fantasy, Star Wars, right? So one of them is like, jump to light speed, you'll get there. How long is it going to take? 10 seconds. Where are we? On the other side of the galaxy. Only 10 seconds, huh? Star Trek. Where are we going? The other side of the galaxy. How long is it going to take? Well, you'll be dead. Your grandkids will be dead. Your great-grandkids will be really old. All right? But the idea is the navigation process. How can you span that? All right? So what is the other side of the galaxy? How do we get there? All right? So spanning real space comes down to the concept of linear algebra. How do you get from one point to another? All right? It all comes down to linear combinations. So one vector is equal to the sum of scalar multiples of other vectors. Well, that's easy. So if I can, so really just consider this. I can define a system where I have 2, we'll call them base vectors. And then every other vector can be redefined in terms of those 2 base vectors. Right, that's a fascinating idea, and I have some examples here, but I'll give you something very basic. All right, just off on the side here, I'll just write it down. Let's say you have a vector and I'll just keep it like very simple. 2, 3. Vector 2, 3. Right. The basis of this real space is now, if you have any experience with vectors, you know where I'm going with this. All right. The basis of real space R2. All right, so 2 space. Is 1, 0, and 0, 1. All right. So I'm going to draw that out on a set of coordinate axes. Very simple set of coordinate axes. Nothing too crazy. Here's the coordinate 1, 0. And here's the vector corresponding to that. Here's the coordinate 0, 1, and here's the vector corresponding to that. So then the question would be, can I define this vector as a linear combination of these two vectors? And all a linear combination is saying is there a scalar, red is where I wanted to go there, that can be multiplied by 1, 0, such that another scalar multiplied by 0, 1 would result in the given vector 2, 3. And just based off of trial and error, you could probably figure it out. I would need 2 of these 1, 0s and 3 of the 0, 1s to get the job done. All right? And so if you start plotting points, here's 2 and here's 3. You could plot it up here. This should be my vector 2, 3. First day of the course, I think, I said that it's going to seem like this course is designed to take very simple ideas and make them sound as complicated as possible. All right, here's an example of that. Because when you learn how to plot points in 2-space, coordinates 2, 3, you were told, take 2 steps to the right, take 3 steps up. If it were negative, you go left or down, and that was it. But now what I'm telling you is, since the basis of real space is vectors 1, 0, and 0, 1, that's telling you that we're counting in terms of what we call unit vectors to get from one location to another, right? So I need 2 of these vector 1, 0s and 3 of those vector 0, 1s to get to that vector 2, 3, all right? But how is that any different from saying, go 2 right and 3 up? It's not any different at all, right? But what we need to be able to do is we need to adjust our thinking, because I could change the basis of real space, and that's where things start getting a little crazy. What if I were to say that the basis of real space was 1, 2, and 4, 7? So now every step, every movement along the x-axis is whatever I said, 1, 2, and every single step on the y-axis is equivalent to 4, 7. All right? So you would realign your thinking, all right? And so that's the important thing to kind of keep in mind, is that dimensional possibilities, they all come down to the fact that perspective is involved, all right? So yeah, you ever hear the old thing of color is subjective? Like, I'm calling this color yellow because I see the color that I'm defining as yellow in my mind, but you might look at it and see it as red, but in your mind, every time you've seen the color red, it was defined as yellow. So you're just calling the thing that I call yellow and you see as red, you call it yellow. All right? Your perspective is different from mine, but we're really talking about the same thing. This is along the same lines as that, except what we're dealing with is I'm seeing one unit, one single unit. If the basis were completely different, let's say the basis is 1/2, 0. All right? The basis of this real space is 1/2, 0. The person who lives in that universe with that base reality is still seeing 1 unit. But their 1 is different from my 1. All right? It's kind of like if I gave you a ruler that was this long and I told you that this is what 1 foot is equal to, and then you measured and developed a measuring system based off of that length. So instead of saying there's 5,280 feet in a mile, you came up with 27,000 feet in a mile, because you call this is your definition of 1 foot. All right, that's what a change of basis does in linear algebra. All right, so in a theoretical sense, it's both fascinating and alarming, scary, intimidating, all of the above, right? But very, very doable. So here's the thing. You get into the mechanics of it, the how, step-by-step process. This is what I'm going to do. I'm going to follow steps. I'm going to get an answer. That buys you time. That's how, I mean, I just assume everybody thinks the way I do. So, and that's dangerous. But at least as a student, it's been a safe bet. It served me well. You learn the steps. You get stuff right. That buys you time to figure out why it all works the way it does. All right, so you're pondering the underlying meanings of all this stuff while you're just getting stuff right. I'll send out the YouTube series. I thought it was really good. It's Essence of Linear Algebra. I forget the title of the channel, but
Oh, is that a 3 blue 1 brown?
that's the one.
Yeah.
Very good. Yeah, he actually talks about basis in there, and it's basically what I said, just he's got cool visuals that go along with it. So,
I'm pretty sure he designed his own engine, actually.
yeah,
Yeah, it's crazy.
it's next level stuff. It's really cool. So I'll send out a link for that so you can take a look at it. It's really fascinating. And if it doesn't motivate you, in all honesty, if it doesn't motivate you to want to study linear algebra, I can honestly say nothing will. You will never be interested in this subject if you watch those videos and you're not fascinated by this.
I was gonna say, can you go, well, I don't know if it has to do with the why, but like with the perspectives and in terms of bases, because I understand that part.
So my little measurement analogy was probably the best one I got. So if you were to say, and actually I think I have half of a ruler, so nothing like a visual aid. Yeah, there you go. This is 1 foot long. All right, now we know it's not, right? But in somebody's reality, in the multiverse out there, so now we're getting like Marvel and all this stuff. It's really enjoyable. So there is a universe out there where this is defined as being 1 foot long. In that universe, they don't think that a mile is 5,280 feet, because this, if it were to cover 1 mile, if they actually had a distance that was equivalent to our mile, it would take a lot more of these to cover that mile than it would a regular 12-inch ruler. So since this is 5 inches, so I'll pretend that it's 6 inches. So let's say that this is half of a foot. So in that reality, they would have to double the 5,280. So we're talking about 10,560. Yeah, 10,560 feet in that universe would be 1 mile, because their basis of reality is completely different. So they've established a different scale for measurement in that reality, and because their smallest unit of measure is measuring a smaller quantity than ours, it's going to change. It's going to have a trickle-down effect to every other unit of measure. All right? So if I go like this, and we establish that that's 5 seconds long, and in another universe there, and that's 5 seconds long for them, then they're compressing time. They're making their passage of time seem like it's faster, all right? But what's gonna happen is they're gonna have a lot more seconds in an hour than we will, all right? So what's gonna happen then is that depending on how many hours that they have in a day, their day may be like twice, 10 times as long as our day because they're counting that much faster. But their reality, it's still the same as our reality. The Earth spins at the same rate. It still revolves at the same rate. It's just their clocks are moving a lot faster. All right? So, but everything is still based off of that. So when they say that it's 36 o'clock, in their reality, they're talking about 7 o'clock here. All right, so it's a new base reality, but it's all determined based off of what you define as your simplest parameter. All right, and that's the main ingredient.
So is it like you're converting other dimensions?
Exactly. That's really it.
Is that a standard base, like 1001?
Exactly. Those are the standard units. All right.
Does it apply to like Fahrenheit and Celsius or metric system?
It could. You could do that because if you're doing any kind of unit conversion from one system to another, that's a change of basis. So we're defining 1 degree. Like, I mean, before there was the name Fahrenheit and the name Celsius, it was just literally 1 degree. And then somebody else said, I have 1 degree also. But my 1 degree is saying, my temperature is saying 0, yours is saying 32. So my basis for temperature is that freezing is at 0 degrees. Well, my basis for temperature is that freezing is 32. Let's build our temperature scale off of that information. All right? So all of these different realities can coexist in the same physical realm. All right? And linear algebra supports all of that. Infinite. So cool. So cool. Yeah, and so all of this is just all the textbooky stuff that takes all the passion out of everything that I just described. So it's like, yeah, and then you can multiply stuff and add them, and you get numbers and things, and it's fun and cool. And it's like, you just ruined it, right? But what this example is actually talking about is real space that is in 3 dimensions. Right, so 1, 0, 0, 0, 1, 0, 0, 0, 1. It's like, oh, you're saying a lot of zeros and ones, but one unit along the x-axis, no movement along y or z. 1 unit along the y-axis, no movement along x and z. 1 unit along the z-axis, no movement along x or z, x or y, I mean. So, put this all together, you have every dimension covered. So, if I were to do any kind of scalar multiple on any of these standard unit vectors, what I would get is the ability to come up with any possible vector that exists in real space, all right? Specifically the 3-dimensional space. All right. So, determine whether B can be written as a linear combination of A sub 1 and A sub 2. Right? So what that's saying is, can I define a set of scalars that would allow for B to result from the sum of A sub 1 and A sub 2. All right? So what I'm going to do is create some arbitrary scalars. I'll call it C. C for scalar. I'm going to say C A sub 1, C sub 1 A sub 1, plus C sub 2 A sub 2 equals B. That's what I'm rooting for. That's what I want to have happen. So from that, I would say C sub 1, because that's my unknown, 1, negative 2, negative 5, plus C sub 2, 2, 5, 6, is going to be equal to 7, 4, negative 3. Now, if I wanted to, I could actually multiply this all out. If I were to do that, I would end up with a system of equations, 3 equations and 3 variables. But I would be going in a big old circle, and I don't want to do that. Right? I'll just talk you through what I'm not going to write down, and then tell you why I'm not going to write it down. So I would get c sub 1 plus 2c sub 2 equals 7. All right, c sub 1 plus 2c sub 2 equals 7. That's kind of like x plus 2y equals 7. Then I would get negative 2c sub 1 plus 5c sub 2 equals 4. That's kind of like negative 2x plus 5y equals 4, and so on. I get a third equation. So you think about what have we done when we had a system of equations? We stripped it down to the coefficients, we row reduced, and then we came up with a solution once we got it into reduced row echelon form. So the big question would be, why would I distribute this all out? Why would I apply the scalars to write it as 3 separate linear equations just to pull out the coefficients when I have them right here? All right. So the idea behind this would be, let's just drop this down into matrix form. All right, so like I said before, we were practicing the skills involved in row reduction techniques. So now what we're gonna do is, okay, we got those techniques somewhat down, but we don't wanna get bogged down with those techniques. So what's gonna happen is, you're gonna follow those techniques only when you're required to. All right, so what that means is that if I don't tell you to do it by hand, you don't have to do it by hand. All right, hugely important, because that's another reason why a person might take 3 hours on a test that should only take about an hour or so. All right, so this is telling you to whip out the old calculator. Back on, because now I have it. Pretty sure it works the same way on the app. I'm gonna sit down from now on. My back is killing me again. So, matrix, menu, edit, matrix A. Oh, it doesn't work the same way. Oh, maybe it does. Let me see. 3 by 3. Okay, it does work the same way. One, 2, 7, negative 5, 2, 5, 4. Okay. So, second, hit the wrong thing. Matrix. So math, reduced row echelon form on matrix A, and we get that, barring any catastrophic miscalculation on my part. Yeah, I'm having a love-hate relationship with this app, the calculator app, because it does almost everything that the handheld calculators do in almost the same way. but it's different enough that I can't just say, all right, everybody, forget buying calculators. Let's just use this app from now on. So it's not quite there yet. 1 year. But it's good enough for a display, so I guess it's $5 well spent by my school district. So anyway, we have a solution here. We just have to pull the meaning from this solution. And the reality is that it's not always the easiest thing in the world to discern, especially since we didn't go through the process of defining 3 separate linear equations. So you're like, possibly, oh, what could the 3 and 2 possibly represent? But really, if you think about it, there's only 2 possible candidates. It's just a question of, well, which one's the 3 and which one's the 2? Well, the C1 comes first, the C2 comes second. If I were to distribute this out, that's the order of the coefficients or the order of the variables within those linear equations. So we can, I think, with a reasonable amount of confidence, conclude that C1 is going to be equal to 3 and C2 is going to be equal to 2. And you could just do a quick eyeball estimate here and just run it through and see. If this is 3, if C is equal to 3, and C1 is equal to 3 and C2 is equal to 2, will that give us a 7 for the first computation? 3 times 1 plus 2 times 2. 7, right? Then you maybe try it for another one. You don't have to do it for every, especially if it's a vector, a column vector that's got like 10 entries in it. You don't want to do it for every one of them. That kind of defeats the purpose of the check. Do it for a couple of them. One, just, get the one out of the way, then maybe do a second one to make sure that maybe you didn't just get lucky on the first one. All right, so 3 times negative 2 is negative 6, plus 2 times 5 is 10, negative 6 plus 5, negative 6 plus 10 is a positive 4. So pretty confident. If you're sitting there taking a test and you got a lot of time on your hands and nothing better to do than check your work, then by all means check them all, but I wouldn't say that it's absolutely necessary. All right.
Is it ever the case that coincidentally all of them could work out except for the last one?
I've never experienced that, but I would imagine that there's like 1 in 10,000, there's that one case, and if you're gonna find it, you know it's gonna be on a test that you're gonna find it, so I guess worst case scenario, check them all. So then the next example is really just kind of talking about the same thing. In the previous one, determine whether B can be written as a linear combination of A sub 1 and A sub 2. Is the vector 4, 5, 5 a linear combination of the vectors below? It's the same question. All right. So that gets a big old star for me, so that you can do that one on your own. One question on there, on that tech assignment, it's really just asking, when that vector shoots out into space, where's it going? All right. If a vector spans all of real space, it must touch every aspect of that reality. All right. So if it's 2 space, then that vector has to hit every little tiny square inch of that real space, that 2 space. Now, obviously, you start increasing the dimensions, you're going to make things more complicated. All right. So you have a vector that's coming out of this corner here, shooting out into space, and I'm telling you, here's our 3 space. That vector, and you use a broom or something, that vector has to touch every cubic inch of space in this room. All right, so it's got to hit every atom that exists in the volume contained in this room. All right, how do you prove that? right? Well, fortunately, we don't have to go atom by atom. We can, if we know the basis of reality, so this is the basis of our system, then we can use our row reduction techniques to make a determination of whether or not you will have a real solution. Because that's the whole thing. I don't need to know what the solution is. I just need to know that a solution exists. All right. So what I need to know in this example here, this really kind of spells it out in 3 space. When I say does S span all of R3, all of real space in 3 dimensions, I'm really just asking, can ABC be written as a linear combination of the basis of that 3 space? All right. So we're basically going to do the same thing we just did. So I'm looking at, some arbitrary constants. And I'm going to call C1 C2 and C3, spoiler. Hi, can I help you? This is not.
Do you know this?
I honestly have no idea, I'm sorry. I wish I did, because I don't. Somewhere in this building, there is a statistics course that's being taught. I hope she finds it. Anyway, so this is what we're looking at. We need to prove the existence of a solution. All right. So we go right on down to our augmented matrix. Now, I throw that little nugget at you a few minutes ago saying you could use your calculator unless you're told otherwise. Sometimes you're indirectly told otherwise. Oh, you put an A, B, and C in the calculator. You're not. All right. So we're gonna have to work this through, but we can handle it. All right. I'm gonna take you through this. I'm not gonna spoil the conclusion. It's just I don't want to give away what we're looking for until it happens or doesn't happen. All right. So we're gonna start row reducing and see what happens. All right. So again, all the different things are in play. You could swap rows, you can multiply by a scalar, or you can use the technique of multiplying and adding. All right. So it looks like I can wipe out both the leading entries in rows 2 and 3 off the bat. So I'll do that first. I'm going to do a -2 R1 plus R2. Simultaneously, I'm going to do a -R1 plus R3. So we're leaving row 1 alone. So the first entry is going to be 0, because that was the whole point. Second entry will be -2. Then we'll have a -1. Fourth entry, a little bit of a different story. It's going to get ugly. Ugly's okay, though.
B minus 2.
Yeah, b minus 2a. Ugly's okay as long as it exists. All right, because we're proving the existence, not anything in particular. We just need to know that there is a solution. All right. So then, last row, 0, 1, -1, C minus A. All right. So, first column, check. Second column, now I want to, again, ideally we get the identity matrix for the 3 by 3, but if not, at a minimum, I want to make sure I have the zeros below all the pivots to get it into echelon form, and then zeros everywhere except for the pivots to get it in reduced echelon form. Right, so I can now start thinking about manipulating some of the other rows. Right, so here I guess I could try to take care of that -2, but then I'm going to incorporate fractions. I don't know if I'm in love with that idea. Right, I can negate row 3 and add it to row 1. If I do that, that's going to get rid of the first entry. It'll make the second entry, it'll make the third entry a little bit more complicated, but at least it'll make that second entry go away, so that's something. The other thing that we can do is have in mind, and so people often forget that swapping rows is a thing. I don't like this as my middle row. I can swap it with the bottom row because that's a little bit more convenient. But what I can do before that is I can kill that -2. And then do the swap, or do the swap and then kill the -2. It really doesn't make a difference. All right. To make it as not complicated as possible, if that's a correct grammatical way of saying anything, I'm just going to do the swap first. So 1, 1, 1A, 0, 1, -1, C minus A, and then 0, -2, -1, B minus 2A. So then what I'll do is 2 times R2 plus R3. So the first 2 rows are going to stay put. 1, 1, 1, 1, 1, 1, 1A, 0, 1, -1, C minus A. The third row is the one that's going to get manipulated. All right, so we're looking at 0, 0. If I take 2, multiply it by -1, I'm going to get a -2, plus the -1 that's already there is going to become a -3. Then algebraically becomes a kind of thing. So 2 times row 2, so 2 times C minus A plus B minus 2A. Simplify if you want, simplify if you need to, or don't. It's up to you, because again, we're looking to show existence of real numbers. So, what does that mean? No undefined, no imaginary. All right, if we avoid undefined and imaginary, then we're accomplishing the goal. All right, at least as far as the numbers are concerned. We also have to be careful about pivots, because if the first pivot value is in the last column, then we got a problem. All right, because that would imply that there's no solution. All right. So if this 3 goes away, this -3 goes away, but we have a value in this last row here, then all bets are off. All right. I'll talk more about that next class. All right. But in my next move, it seems like I'm probably going to want to divide that last row by a -3. So maybe simplifying is the way to go. So I'm just going to do it off on the side here. 2c minus 2a plus b minus 2a, which all simplifies down to 2c minus 4a plus b. Any order you want, it doesn't really matter. All right, just make sure if you move things around, bring the signs with them, obviously, but aside from that, it's okay. Let's see. Yeah, I think our next move is to divide by 3. So 1/3 of row 3. So just all that stuff over 3. So that's something. I mean, it's a lot to write, but at least it's not stuff you have to think about. Oh, sorry, -1/3. Because we want it to be a positive 1. All right, so I'm going to put it over a -3 because I don't want to have to worry about distributing the sign, aka I forgot. So I don't want to have to erase everything I just wrote. All right, we can actually wipe out the -1 in row 2 now by adding row 3 and row 2, which is one of those things where you're like, that was the one thing I was hoping I wouldn't have to do. But that's what needs to happen, so, or it's one of the things that needs to happen. Row 3 plus row 2. So 0, 1, 0, all that stuff added together. Again, I'm not simplifying unless I have a dang good reason to. So c minus a, I can write, instead of plus, I can write minus, and then the whole fraction, 2c minus 4a plus b all over 3. And then the bottom is going to be what it was, 0, 0, 1, and then all that stuff again. Here I think I might just negate the numerator just to clean it up a little bit. So 4a minus b minus 2c all over 3. All right, eventually we're gonna have to do something with row 2 because I want to use that on row 1 to get rid of that middle entry. So it's gonna happen. It's just a question of do I want to clean it up now or do I want to clean it up later? You know, it's kind of up to you. But you know, on the side we could just do the work to clean it up and then just leave it in the matrix the way it is. So with a common denominator, I'd be looking at 3c minus 3a minus parentheses 2c minus 4a plus b all over 3. So we'll have a c. Negative 3 plus 4 is a, so plus a. And then minus b over 3. Which is actually, I don't want to say shockingly simple in comparison, but it's definitely simpler. Right? So when we go through the process of working this against that, it'll be a little bit easier. So that's something. Little side work. So, but what I wanted to do is my next step, and you might disagree, you might want to do something different, and that's up to you, but my thinking has me working with row 3 on row 1. So negative row 3 plus row 1. So second row is going to remain unchanged, but I'll write my new expression in there. I'll write it as a minus b plus c. Over 3. And then 0, 0, 1. And then 4a minus b minus 2c all over 3. So then I just got to work row 1. If I'm negating row 3 and adding to row 1, it's going to be 1, 1, 0. Now this whole thing is getting added to a. All right. You could do that some on the fly, I think, because I can actually just manipulate the a right now and just call that 3a over 3. Because I would need a common denominator. So if I'm going to add these two together, negative b and c are going to remain the same. I'm just going to take the 3a and add it to the a that's already there. So it's going to be this same fraction. Oh, sorry, I was looking at the wrong thing. You're going to have the negative b and the negative 2c are going to remain the same. So I'm just adding the 4a and the 3a. So it's going to be this same fraction, just instead of the 4a, it'll be a 7a. All right. So little things like that can make a big difference. And then the last step has us, and by the way, we know we're still in good shape because my denominator is only a constant 3. There's no variable in the denominator. So I don't have to worry about any circumstance in which this is going to be undefined. All right? And it's also looking like we're going to get the identity matrix. So as long as we can avoid a variable in the denominator of the fraction, we're going to be golden. We're not going to be looking at any instance in which this would fail. All right? And we'll have a legitimate proof. So the last thing that we need to do is negate row 2 and add it to row 1. So negative r2 plus r1.
Could you negate row 3, the ABC before adding to A?
Schnitzengruben.
Yeah, so it should be 1A.
It should be 1a and then plus, right?
Plus B
Plus b plus c. Thank you. Then of course there's that, like calculations and stuff. Good.
Doesn't it check?
Minus
I have a negative 1/3 on the outside, then a plus b plus 2c.
So you have a negative.
Yeah.
it's a negative a, right? Because it's 3a minus 4a.
3a minus 4a, so negative, yeah. And then it's negative this whole
It
thing.
could be a negative a minus b minus 2c. Or you factor out the
Right.
negative and put it on the outside. and then it's positive.
So we negated this, so that changed all these signs. Then we added the 3A, so
Negative 1/3.
Negative A plus B plus
N-
2C.
So negative A, then plus, then plus, right?
Yeah.
Okay. Okay, now we got it. Okay, so then the last move, negate row 2 and add it to row 1. So we're looking at the identity matrix, so that's fine. And so we really only have one challenge ahead of us to make sure I don't screw up this next part. All right, so I know it's gonna have the common denominator, so that's the one good byproduct here. We're negating and adding. So if I negate this and add it to that, negative 2A, negate this, it becomes positive B, plus B becomes 2B. Negate this, add it to that, negative 1 plus 2 becomes 1, so 1C, so plus C. So the solution exists. Therefore, S spans the set of all real numbers in 3 dimensions. That's a lot. Look at that. All right, and again, all we were looking for was existence. All right, so C1 is equal to that, whatever that is. If you knew what A, B, and C were, then you would know what that is. C2 equals that, C3 equals that. All right, so we now have, well, we already knew the basis for this reality. These solutions give us the formula to navigate that reality.
What would like a non-solution look like? What would it look like if it like weren't to span that thing?
You would get all zeros here and then a value in that last column.
Okay.
Because what you end up with is a contradiction somewhere. Anywhere that there's a contradiction means that there's no solution.
But what if it's like all zeros?
If it's all zeros, then that's fine. Yeah.
Okay.
So yeah, so all you're worried about whenever you're row reducing is making sure that you don't get a pivot value in the last column. All right, if there's a pivot value anywhere except for the last column, you're good. But if that first non-zero entry in any row, if that first non-zero entry hits in the last column, no solution. All right. So yeah, it's the terminology sometimes more than anything else, but that's really the long and short.